Hey everybody, welcome to the Unknown Mixture Lab. Here's the outline for this video. I'll be spending a good time going over a flowchart showing how to separate two unknown compounds from each other, in this case some unknown alcohol from some unknown acid. And during that, I'll also be going over the phenylurethane derivative reaction and the titration procedure, after which I'll show the actual experiment in the lab. So for this lab, we'll be given two compounds mixed together. We'll be given one of these 6 alcohols mixed with one of these 6 acids. And our job is to separate the two from each other and characterize them so we can figure out which two we were initially given. All of the alcohols and the acids are solid at room temperature, so we'll be given a test tube that has a whitish powder in it, which will contain one of the alcohols and one of the acids. What I would do before even considering any chemistry or any separation process is to look at the compounds themselves and start considering things like solubility or pKa values or any other properties that would be helpful in the separation process. So here are all of the possibilities for the unknown alcohol and all of the possibilities for the unknown acid. Now, we don't know which compounds we're going to be given. So from here, we had to create a flow chart that would work in separating any unknown alcohol from any unknown acid. You can use the Cannizzaro lab procedure as a reference, since in that lab we separated an alcohol product from an acid one. But in this flow chart, we'll be making some adjustments and some changes since we want to create a general flow chart that would work for separating any mixture. The first thing we can do is to dissolve the two compounds in an organic solvent. So methylene chloride is a great choice. We've used that very frequently in the lab. Some acids might not be very soluble in methylene chloride because they're more polar, and we'll see them persisting as a solid even though we've added a good amount of methylene chloride. If this happens, we can continue the procedure just fine, but I'll come back to this scenario in just a second. Once we've dissolved the two compounds, we can add an aqueous base, which will create a bilayer and ionize the acid so it'll move it into the aqueous phase, separating it from the alcohol in the organic one. Now, as to which base to use, we could try using sodium hydroxide, or we have also used sodium bicarbonate as well. The thing we had to be concerned about is deprotonating the unknown alcohol. Since two of them are phenols, they would have a much lower pKa than other alcohols and would be at a higher risk of being ionized as well and following the acid into the aqueous layer. That means we'll want to use a weaker base that won't react with these alcohols, so sodium bicarbonate is a great choice for that. Once it's added, we'll see the bilayer formed and the acid will start moving into the aqueous layer as it's deprotonated, and we'll also see CO2 bubbles coming off as the sodium bicarbonate reacts. This is something to watch out for because once the CO2 bubbles stop forming, it means one of two things. Either the acid has been completely reacted with and is fully in the aqueous layer now, or all of the sodium bicarb has been used up and there's still neutral acid in the organic layer and we just need to add some more sodium bicarb. We do want to be careful here though because we don't want to add too much sodium bicarb and introduce too much water because some of the acids may be somewhat soluble in that aqueous solution, especially this one. With that many polar hydrogen bonding groups to that many carbons, it's going to be fairly soluble in water, and we might have difficulty getting it out of the aqueous solution, even when we neutralize it later on. For this reason, we'll be doing the separation in a polypropylene test tube so that we can cap it and mix the two layers together really well by shaking it. Then we can watch for those bubbles and even open the cap to listen for any gas that might come out. Be mindful that methylene chloride evaporates pretty easily and can start evaporating just by absorbing the heat from your hand. So just because we hear some gas coming out of the test tube when we open the cap doesn't mean that it's coming from the sodium bicarbonate reaction. Usually the CO2 bubbles come off after the first 2 or 3 shakes, and we'll hear a more prominent fizz upon opening the cap after those first 2 or 3. After that, if we hear a small fizz after shaking the test tube, it'll most likely be coming from the methylene chloride evaporating. Now, if we end up in this scenario where the acid doesn't dissolve very well in the methylene chloride, we can still get to the same spot just by adding sodium bicarb. As we shake up the test tube, the sodium bicarb will eventually react with all of the acid and dissolve it in the aqueous layer, getting us to the exact same spot as if the acid had been soluble in methylene chloride. Once we're here, we'll separate the two phases, making sure to keep both of them, and it's possible that some of the alcohol may be somewhat soluble in water, especially this alcohol. So to make sure that we get all of it into the organic layer, we'll extract the aqueous layer 3 times with methylene chloride, combining it with the original organic phase. We don't have to worry about the acid moving into the methylene chloride during those extractions. Because it's ionized, it won't want to interact with the organic solvent at all and will remain in the aqueous layer. In the Cannizzaro procedure, the organic extracts were rinsed with sodium bicarbonate after separating them from the aqueous phase. But the only reason that we would do that in this lab would be if we didn't use enough sodium bicarbonate initially and there was still some neutral acid left over in the organic phase. So this part is kind of left up to the students to decide whether or not they want to rinse the organic layer with sodium bicarb. The thing we're worried about is the alcohol being somewhat soluble in water and moving into the aqueous layer right after we just separated it. If we do decide to do the rinse, we'll want to use a conservative amount to minimize the risk of losing any alcohol product. And if there's no acid, we won't really see anything happen, just the bilayer form. But if there is acid left over, we'll see some CO2 bubbles as the acid reacts and moves into the aqueous layer. Either way, we'll remove the methylene chloride layer after and dry it with sodium sulfate. Then we can evaporate the solvent to get the crude alcohol and recrystallize it so that we can characterize pure crystals and get an accurate melting point range. The problem here is that we don't know which alcohol we have, and therefore we don't know which solvent would be best to use in the recrystallization process. In the past, we've used Lagroin, we've also used ethanol and water, and we could even use an ethanol-water mixture if either ethanol or water doesn't work out too well. In the Cannizzaro lab, Lagroin was used as the solvent to recrystallize the alcohol product, so generally that's a safer choice in recrystallizing the unknown alcohols. But to be safe and to figure out which one would really be best, what we'll do is separate a little bit of the crude product into 3 separate test tubes, and in each of those, recrystallize the crude alcohol using one of the 3 solvents or an ethanol-water mixture. Whichever one ends up working best, we'll just use that solvent to then recrystallize the rest of the crude alcohol. Once we've separated those crystals, we can then obtain the melting point range and compare that to the literature values on the table. Now, when taking the melting point, what I would do instead of waiting between 54 and 142 degrees to see where it melts is to place it somewhere in between values and see what happens. For example, I would place it in between these 2 values, say like 100 degrees Celsius, and if it doesn't melt, that means it has to be one of these 2 compounds. But if it melts instantly, that means it's going to be one of these 4 compounds. Then I would probably put it in around 60 degrees, and if it melted pretty quickly, it would probably be one of these 2, and you could start at 54 degrees or a little bit below and ramp the heat up to see exactly where it melted. If it didn't melt, then it's most likely one of these 2. It's possible that we would get a very, very pure 1-octadecanol that wouldn't melt, but more likely it's going to be benzhydrol or the 3,5-dimethylphenol. Once we've acquired the melting point range, we'll use 100 milligrams of the remaining crystals to form a phenylurethane derivative. And this is kind of how that will work. The alcohol will react with phenyl isocyanate and form this phenylurethane derivative, which is a different solid from the original unknown alcohol and has varying melting points depending on the R group that was attached to the alcohol. The literature values for the melting points of the derivatives are given in the table as well, and we can compare the melting point that we get for the derivative to the original melting point that we took for the unknown alcohol to figure out exactly which alcohol we had. This will be really helpful in distinguishing compounds that have similar melting points, like these 2. For example, if we got a melting point between 65 and 66 degrees Celsius, it could definitely be benzhydrol, but it could also be a slightly contaminated 3,5-dimethylphenol. But the second melting point of the derivative can really help in clearing the ambiguity that might exist there. We have to be careful of having water contamination here though, because obviously water has OH groups as well and can react with the phenyl isocyanate to form this diphenylurea impurity, which has a melting point of 241 degrees and can definitely contaminate the urethane derivative that we would want. So before doing this reaction, we'll dry the crystals really well to make sure that there's no water contamination before doing this. To help get rid of water, we'll also be placing the conical vial and the spin vane that we'll be using in an oven for about 15 minutes just to make sure that everything is nice and dry. For that reaction, we'll dissolve 100 milligrams of the alcohol in methylene chloride, then add phenyl isocyanate and a drop of pyridine, which will act as the catalyst for this reaction. And then after an hour and a half, we'll add a few milliliters of hot ligroin, which will help crash the urethane derivative out of the solution, and then we can remove the derivative and characterize it by taking its melting point, then compare it to the melting point that we took for the unknown alcohol. If we did a good job, this should give us a pretty good idea of which alcohol we have, and we can write that in our conclusion. Now, as for the acid, we have it dissolved in an aqueous solution, so we'll want to add a concentrated acid like 12-normal HCl to neutralize it. We want to use a more concentrated acid because if we use a more dilute one, it'll require more solution to completely neutralize the unknown acid, and that'll introduce more water, and if our acid is soluble in water, that could cause problems. As the hydrochloric acid is added, we'll see CO2 bubbles coming off as it reacts with the sodium bicarbonate, and eventually the unknown acid will precipitate out of solution as a white slurry, and we can test the pH of the solution to make sure that it is acidic. That way we can know that the unknown acid is fully neutralized. At this stage, we'll want to make sure that the solution is stirred very well because there might be some base remaining that is unreacted, and upon stirring it, the hydrochloric acid will react with that, more CO2 will come off, and the unknown acid could redissolve into that solution. Upon checking the pH, we'd see that it might not be fully acidic, and we'd have to continue adding acid until it was. If we end up with an acid that is soluble in water, we might not ever see a precipitate form, even though we stir it for a long time and the solution remains acidic. If this ends up happening, there is something that we can do, but I'll come back to that in a second. Once we have the neutralized acid, we can remove it from the aqueous solution and then recrystallize it to get pure crystals that will give us an accurate melting point. And again, we don't know which acid we have, so we can do the same thing that we did with the unknown alcohol, separating a small portion into 3 separate test tubes and testing the solubility with the 3 different solvents. Whichever one works best, we can use that to recrystallize the rest of the unknown acid, and then once we have the crystals separated, we can characterize them by taking a melting point. Now, if we ended up in this situation where we never saw any precipitate form, then we can place that solution in an ice bath to see if we can help any of that acid come out of solution. If this happens slow enough, then we actually don't have to recrystallize the solid afterward because it would have already undergone that process by coming out of the solution slowly. If that's the case, then we can simply remove the crystals and characterize them by taking a melting point. If it comes out of solution too quickly, then we might have to recrystallize it afterward, and if it doesn't ever come out of solution, then we'll probably have to start over, being more careful of how much sodium bicarb and aqueous solution we add. After acquiring the melting point, we can take the rest of the unknown acid crystals and use them to perform a titration. To do that, we'll accurately weigh around 50 milligrams of the unknown acid and dissolve that in 15 to 20 milliliters of water. If it doesn't dissolve in that much water, then we could try an ethanol water solvent system. For that, we would dissolve the acid in a minimum amount of ethanol, heating it to make sure that it did fully dissolve, then add enough water to make the solution at least 50% aqueous. Once the acid is fully dissolved, we'll add a drop of the phenolphthalein indicator, and we'll want to make sure to do this or else nothing's going to happen. The solution won't change color, and most likely we'd have to start over. Once that's all ready though, we'll start adding the standardized sodium hydroxide, which is usually around 0.1 normal, but the stockroom will give us a specific one, and we'll add that to the solution using a burette with a stopper so that we can add it dropwise, and we'll add that just up until the solution turns and remains a light pink color. This will mean that the base has just reacted with all of the acid in there, and we can then measure the amount of base used in milliliters. Once we have that data, we can find the neutralization equivalent by taking the weight of the unknown acid in milligrams and dividing it by the milliliters of base used times by the normality of that base. We can then calculate the molecular weight of the unknown acid by multiplying the neutralization equivalent by the number of acidic groups on the compound that we think we have. We can then compare that number to the molecular weights of the unknown acids and to the melting point range that we obtained earlier. So I'll show a quick example of how this can be helpful. Let's say that we get a melting point range for the unknown acid from 131.9 degrees to 133.2 degrees Celsius. So that looks to be right in the range for cinnamic acid, or in the range for a slightly contaminated sebacic acid. We then run the titration, weighing out 56 milligrams of the acid and using 4.8 milliliters of 0.120 normal sodium hydroxide, which would give us a neutralization equivalent of 97.22. We look at cinnamic acid and see that it has one acidic group on it, so we would multiply the neutralization equivalent by 1 to get the molecular weight and compare that to the molecular weight of cinnamic acid, which is off by a bit. So we could look at sebacic acid and we can see that there are 2 acidic groups on it, so we would multiply the neutralization equivalent by 2, which is a lot closer to the molecular weight of sebacic acid, so the data from the titration would be leaning towards sebacic acid rather than cinnamic acid. From here though, deciding on which acid we actually have kind of depends on how well we feel like we did the titration versus how well we feel like we isolated a pure crystal to take an accurate melting point. That's kind of up for the student to decide. So once we have the data for the acid as well as for the alcohol, we're going to make our best educated guess based off of how things went in the lab. Once we think we know which compounds we have, we'll write those in our conclusion along with the reasons why. And then the second part is to look at the bottom of the procedure through all of the NMRs and find the ones that we think match up with the 2 compounds that we had. Then we'll draw the molecules and label the peaks just like we've done in all of the other labs. When labeling these, be aware that the NMRs were done with dry solvents, which allow coupling between alcohol groups and neighboring hydrogens, which we haven't really seen before. So we'll actually see splitting for the alcohol peaks, and they'll also cause splitting for neighboring hydrogens as well. So here's the mixture. I've already placed it into a polypropylene test tube, and now I'm going to start adding the methylene chloride to begin dissolving the compounds. And I added around 4 to 5 milliliters just to allow the compounds enough space to move around once I start mixing the 2 phases together. Then I'll add 2 to 3 milliliters of sodium bicarbonate, which should be enough to deprotonate all of the acid, but not too much just in case I have an acid that is soluble in water. Now I'll place the cap on the test tube and shake it up so that the 2 phases can interact together really well. And you can kind of see the CO2 gas coming off as the sodium bicarb reacts with the acid, but I'll also open up the cap and listen for any gas released, and there definitely was some fizzing, so that means the reaction is happening. I'll continue to shake up the test tube a few more times, watching for those CO2 bubbles, and also cracking the cap to listen for the gas. There's only some slight fizzing now, so we're probably good to move on. So now I'll remove the organic layer from the aqueous one, and then extract that aqueous layer 3 times with some additional methylene chloride. Once those extracts are gathered, I'll dry them over sodium sulfate, and I'll add that until it's free flowing. Then I can remove the methylene chloride solution and rinse the remaining sodium sulfate with some additional methylene chloride to reclaim any unknown alcohol that would have been left behind. The methylene chloride solvent can then be evaporated using a stream of air and gentle warming, and this is what the crude alcohol ends up looking like. I'll gather it so I can begin the recrystallization process, separating a small portion of it into 3 separate test tubes in order to test out which solvent is going to work best for recrystallizing this unknown alcohol. Here are the three solvents that I'll be testing. I'll try Lagroin, 95% ethanol, and water, and possibly also an ethanol water mixture. When I put the first test tube in, the solid just melted, which is actually a pretty good indication that the alcohol I have is one of the four that has a melting point below 100 degrees Celsius. But from here, I will be careful to monitor the temperature of the water so that it doesn't get too hot. I'm going to keep the temperature around 50 degrees just in case I do have the one with the lowest melting point, and I'll place a thermometer in the water bath to make sure it stays around there. The first solvent I'll test out will be water, so I'll add that with some stirring to try and dissolve the solid. But it was pretty obvious after a little bit that it's not dissolving in water even after I've added a bunch, so I'm going to try out a different one. Next, I'll test ethanol to see if that works better. And it looks like the solid dissolved in a really minimal amount, so I'm going to test to see if that even comes back in an ice bath. I put the test tube in there for a few minutes, moving it around, even scraping the sides of the glass with a spatula, and nothing came out of solution, so straight ethanol is probably not the best solvent to use. I might be able to use a water ethanol mixture, but first I want to try out using Lagroin to see if that works better. I'd imagine that this nonpolar solvent would work pretty well since the solid was not soluble basically at all in water. So I'll keep adding the Lagroin with some stirring to see if it dissolves. And it looks like it did get there eventually. So now I'll test that it can come out of solution in an ice bath. And that worked great. It looks like Lagroin is the solvent of choice for this alcohol, so I'll go ahead and add the rest of the unknown alcohol to a Craig tube and begin dissolving it in Lagroin. Once it's fully dissolved, I'll confirm that it can still come out of solution in an ice bath, which looks like it still can, so I'll redissolve it in the hot water bath and then leave it at room temperature so that the alcohol can recrystallize slowly. I'll remove those crystals using a stopper and polypropylene test tube, and I'll place it in the centrifuge for a few minutes. Now I can remove the pure crystals and see where this alcohol's melting point is. I initially put it in right around 60 degrees Celsius since I already know that it's going to be one of the four lower melting points. And nothing happened, so I'm going to slowly start raising the temperature to see exactly where this melts. And I started seeing it melt around 64.7 degrees Celsius, and it looks like it completely finished around 65.9 degrees Celsius. Now that the melting point has been obtained, I can start the derivative reaction by heating up a conical vial and a spin vane in the oven for 15 minutes. Then I'll weigh out 100 milligrams of the unknown alcohol crystals and add that to the dry 5 milliliter conical vial. I'll get some dry methylene chloride from the hood and add that until the solid is completely dissolved. And it shouldn't take any more than a milliliter. Once that's ready, I can add 1 drop of pyridine and then 100 microliters of phenyl isocyanate. Now I'll just cap the vial and let that react for an hour and a half. While that's going, I'm going to go ahead and start working on the unknown acid. So I'll get the 12 normal hydrochloric acid to begin neutralizing the solution, and I'll add that until the solution is acidic. You can see the CO2 bubbles coming off as the hydrochloric acid reacts with the remaining sodium bicarb. And remember that we want to be stirring this really well so that the hydrochloric acid is able to react with everything in there. After a little while, I'll go ahead and test the pH to see where we're at. and it's not quite acidic, so I'm going to keep adding the hydrochloric acid and keep spinning it until we see precipitate forming or the solution is fully acidic. At this point, I'm seeing fewer bubbles when I add the HCl, almost none, so I'm going to go ahead and test the pH again. This time it is acidic, but just in case, I'm going to allow the solution to spin for a while longer to make sure that the HCl has reacted with all of the base. And I have yet to see any precipitate form, so this unknown acid has got to be very soluble in water. If the solution remains acidic and no precipitate has formed, I'll have to put it in an ice bath to try and get the product to come out of that solution. And it is still acidic, so I'm going to go ahead and transfer the solution to a test tube now and place it in an ice bath to see if I can get that unknown acid to come out. After moving it around for just a little bit, nothing happened, so I'm going to leave it in there for a few minutes now just to see if anything does change. It's kind of hard to see, but after about 5 minutes, some crystals started forming at the bottom and at the top, and eventually started recrystallizing really nicely. After the solid has completely formed, there's actually not going to be any need to recrystallize this acid because it already did that, coming out of the water solution slowly. These crystals should be pretty pure. I'll remove those crystals using vacuum filtration and rinse the crystals using some ice cold water, being very careful because obviously this acid is pretty soluble in water. And I'll stir them around on the Hirsch funnel to make sure they're nice and dry. Once dry, I'll remove the crystals from the Hirsch funnel and see where they melt. I first put them in around 175 degrees and they melted instantly. So then I put them in around 140 and nothing really happened. So I'm going to go ahead and start ramping up the temperature to see if I can get their melting point. And it looks like everything started melting around 148.1 degrees Celsius and finished around 150.1. Now that I've got the melting point range, I'm going to start the titration by weighing out the unknown acid that I have left. And I'll want to do this as accurately as possible so that I can also get an accurate molecular weight to compare to the melting point range. I'll add these 75 milligrams of unknown acid to a 100 milliliter beaker and start adding the water to dissolve it. Once there's enough water, I'll make sure that the spin bar is going so that it can help dissolve that solid. And although it was super soluble in water before, it seems like it's not quite there yet, so I'll add a little bit of ethanol to help. But eventually it looks like it did fully dissolve in that water bath. I'll make sure to add the phenolphthalein indicator so that we know when the titration is done. And this is the burette that I'll be using for the titration, which is currently just filled with water, so I'll go ahead and remove the cork and open the stopper at the bottom so all of the water can be drained out. Once that's done draining, I'll close the stopper so that I can then add the standardized sodium hydroxide, which has a concentration of 0.181 normal. And I'll add that through a funnel at the top of the burette, being careful to accurately note exactly where the sodium hydroxide reaches in the burette so that I can measure exactly how much base is used in the titration process. I'll set up the burette above the beaker with the dissolved unknown acid, carefully opening the stopper so that the base can start coming out slowly dropwise. And initially there's no pink color as the droplets hit the aqueous solution, but eventually some pink color starts to linger as the base is added, so I'll want to slow things down a little bit as that starts to happen. Eventually the solution remains a pale pink color, and I continue to stir it just in case there is some unreacted acid in there, but after a few minutes it looks like it's going to remain that pink color. So the titration is done. And here's where the sodium hydroxide ended up. So it looks like only 3.4 milliliters of base were needed. Now I can drain the remaining sodium hydroxide in the burette out. and rinse it with water afterwards to make sure that all of the sodium hydroxide has been removed. After all of that, the derivative reaction is now done, so I'll prep some Lagroin by placing it in a test tube and putting that in a hot water bath to heat it up. Then I'll remove the cap from the conical vial and start adding the Lagroin until the solution reaches a total of 4 milliliters. And as I continue to add it, you can actually start to see the derivative solid coming out of solution. So I'll remove that from the solution using vacuum filtration. And I'll rinse the conical vial with some cold Lagroin, also rinsing the spin vane and the derivative on top of the funnel with Lagroin as well. Once it's been allowed to dry for a few minutes, I'll go ahead and remove the derivative from the funnel and find out where its melting point is. I first placed it in around 165 degrees Celsius and it melted really quickly, so I then put it in again a lot lower, around 110 degrees Celsius. And nothing happened, so I started it again, this time around 135 degrees, letting it warm up. This solid started melting around 138.6 degrees and finished around 140.1 degrees Celsius.